Hi everyone, I am Alessandro Epasto, and today I'm going to present a joint work with other Googlers, Silvio Lattanzi and Renato Paes-Lemer. So in this slide, I'm showing you how a social network or any graph should look like for the purpose of clustering or community detection in graphs. And as you can see in this ideal world, we have that there are communities that are completely disjoint, so there is no node that belongs to two different communities. And there is a sparse cut between these communities. So there are not many edges connecting these two communities. And moreover, each cluster is very dense. There are a lot of edges inside the cluster. So this is, if this is the case, you can take any of the tons of algorithms that have been defined for a non-overlapping community detection, and you will most likely find the correct clusters. And there are also some of these algorithms that have provable guarantees. However, the real world is much more complicated, as we have been observed during the years studying this problem. And in particular, what it has been found is that in real world graphs, you have that the clusters are connected by a lot of edges. So there is a large cut. Even worse, these clusters are not even disjoint. So there are nodes that belong to multiple communities. So these increase even more the number of edges that connects these two cuts, and there are also nodes that connect them. And finally, even more worrying, there are more connections outside of the cluster than there are inside of the clusters. In fact, if you think about your social intuition of your life, if you think about your family, you probably know more people outside your family than you know inside your family. So it's totally normal that there are more connections outside than inside. This, however, completely defeats most of the assumptions of the entire literature, and this has been observed for many years. It is known that there is no clear microscopic structure of clusters in social networks or large-scale graphs. It is very hard to find large clusters, but even like the small ones are difficult to find. And even worse, it has been observed that if you ask users to label communities, these communities will look very differently from the ones that are found by the algorithms designed to find them. So the problem is very hard, but it's also very important. But there is a good news. So the good news is that if we look instead of the simple problem of clustering the local structure of near a node, the problem becomes much simpler. And to explain this, I will first introduce the concept of egonets. So what is an egonet or an ego network? It is a subgraph of a given graph defined for the specific node. So for instance, let's look at the red node in this slide. The ego network of this node is defined as the subgraph that contains this node, all the neighbors of these nodes, and all the edges among these nodes. Okay, so these the blue edges and the nodes there are the ego network of this red node. And for the rest of the talk, I will assume that the graph is undirected and is unweighted, but you can define this in directed graph, and etc. etc. So this is a very simple definition. We will need to use a slightly modified definition of ego network, which is usually called the egonet minus the ego. Here, this egonet minus the ego for a given node U is defined as the subgraph containing only the neighbors of U, so not U, only the neighbors, and only the edges among the neighbors of U. Now, for simplicity, from now on, when I will say the word egonet, I mean this, the egonet minus U. Okay. Now we have these two definitions. Why is this interesting from the point of view of graph clustering? The reason is that if you look at this slide, you can see that at the level of the ego network of a node, so the egonet minus ego, please remember it's the egonet minus ego, it is very easy to find these two clusters. You can even use, in this case, the connected component algorithm, and you will find two groups of nodes that are completely disconnected among themselves. And you can imagine that perhaps these are like the work community of this node and the family community of these nodes. And if you look at your social intuition for your real world life, you will see that this is probably happens. So this is very interesting. And the reason for which this happens is that essentially, while nodes belong to multiple communities, pairs of nodes usually belong to a single community. So there is usually one reason for which you know all the person that you know. So this has been studied for quite some time. The word egonet has been defined in a sociology paper in the 80s. This is part of the data mining and machine learning community. And for the purpose of clustering, the use of a connected component inside the egonet has been tried for 2010 by Rees and Gallagher. And this has been then improved by using clustering algorithms at the level of the egonet in a second paper by Kosha and others, where they introduced the demon algorithm. And there are many other follow-ups on these problems, including machine learning-based applications. So this has been studied for quite some time. But our contribution now is that we define a novel method for overlapping clustering in graphs, which we call Egosplitting. And this method is highly flexible. So it allows to transform any non-overlapping clustering algorithm into an overlapping clustering algorithm. And this is very useful because there are way more non-overlapping clustering algorithms than there are in overlapping clustering algorithms. Contrary to many of this previous work, this is extremely scalable. So it can run on graphs that have tens of billions of edges and nodes. And this, of course, is done through parallelization and distribution of the work. And it has also provable theoretical guarantees. So we will see that in some specific probabilistic model of graphs with ground truth communities, we can provably reconstruct correctly these communities. And fourth, and I think this is the most interesting part of this work, is that this framework is based on a novel graph theoretic concept, which we call the persona graph of a graph, which I believe it could can have many other potential applications besides that of overlapping clustering. So I think this could be quite interesting. So before defining our framework, I will give some intuition for this persona graph, which is the basis of our overlapping clustering algorithm. So what is the persona graph? As I said before, looking at the EgoNet of this node, we can imagine that there are these two communities which represents, for instance, the work and the family communities of this node. Now, what that means is that in this graph, this node plays two roles. So it's actually two distinct nodes. So the simple idea that we have, which is a very simple idea, is that why don't we just create two nodes for this node? And we will call these two nodes the persona nodes. Okay? So what we do, we simply split this node in two parts. We create two nodes, one that represents the instantiation of this node in one community, let's say the work community, another that represents the instantiation of these nodes in the family community. And now we have a new graph, which we call the persona graph, where each node in the original graph is split or not, it depends on the situation, in multiple nodes, which we call the persona node of the original node. Notice that in this graph, once we create these new nodes, we can also easily assign the original edges of this graph to one of these persona nodes, because the original node had 6 edges, with 3 of them were directed towards the work community and 3 of them were directed towards the family community. So now now we have created these two nodes, we can simply split these edges to 3 edges towards the work community, the work node, and 3 edges towards the family nodes. So this gives the intuition for our framework. I will now give an overview of how this works. This works in a series of steps. The first step is creating, of course, the EgoNet of each node in this graph, and this can be done in parallel efficiently, as you can see later. Then we apply any non-overlapping clustering algorithm over each individual EgoNet. Let's call this the algorithm A1. This allows us to create a new graph, which is the persona graph of the original graph, and of course depends on the clustering algorithm. Then we will partition this persona graph using another clustering algorithm, a non-overlapping clustering algorithm. Let's call this algorithm A2. And finally, based on these non-overlapping clusters of the persona graph, we will obtain overlapping clusters of the original graph. Now, let's look more precisely at how the persona graph is defined. Here is an example of the original graph, which is undirected for this talk. Now we construct the EgoNets of some example nodes. What is the EgoNet of node C? Is simply the list of the neighbors and their connection. Now, since we need to use a clustering algorithm to have a good intuition of how it works, I will assume that the clustering algorithm we are using is the simple possible clustering algorithm, which is the connected component. So now you can see easily that node C has 2 components, and so 2 clusters, one with A, B, and the other with E, F, and D. And for instance, node D, instead, we have only 1 component. So what will happen in the persona graph? Node C will be split in 2 different persona nodes, and node D instead will not be split. Now we have created a graph where you can easily assign certain nodes to each original nodes, and you need just to match the edges. Among these persona nodes, so the original nodes needs to be assigned to edges to specific persona nodes. But this can be done very easily, as we will see later in the slides. In fact, more precisely, what we do is the following. So let's assume that for a node U, we have partitioned the EgoNet of U in T of U clusters. Now we will create exactly T of U persona nodes. And each of them is associated uniquely to 1 cluster. So now, how can we match the edge UV with a specific persona nodes of U and a specific persona node of V? Very simple. Because let's look at the EgoNet of node U. There is only one cluster to which the node V belong. Let's say that this is the cluster I. So now we know that the persona node, the ith persona node of U is the one that is really associated with V. So we will associate this edge UV to this persona node of U. And you can do the same for node V. And so this precisely define the persona graph. Now that we have this graph, we can apply, as I said, any clustering algorithm, and we get partitioning of the persona nodes. Since each node belongs to multiple personas, potentially, if you remove this persona identifier and you look just as the original nodes, this induces naturally an overlapping clustering over the original nodes in the graph. So this is just like our algorithm. This is a very simple idea. Now, of course, you might wonder whether this is feasible on very large graphs because it seems to be a complex procedure. And if you do that like in a very naive way, this will take n squared time. However, as we have already shown in a previous paper, it is actually very efficient to construct the EgoNets and cluster them. And in particular, it is as efficient as computing the triangles in graphs. And trust me, there are tons of papers on counting and enumerating triangles. So this can be done very efficiently. And there are more details in our paper. So why this is related to triangles and why this is all very related to triangles, the intuition is just that if the edge UV is part of the EgoNet of Z, that means that there is a triangle, UV and Z. So you can see that there is a direct connection between these two things, and this allows to parallelize and distribute the work in a very efficient way. This is for creating the EgoNet and clustering, but you can see that we can do basically the same also for the entire pipeline of our work. So what we show is that for instance, using MapReduce, you just need the order of 4 rounds of MapReduce to completely create the persona graph and cluster it. And the total work that will be needed is order of m to 1.5. And of course, this depends on the clustering algorithm that you will use in the node, but this is the relationship that you have. And this could be, of course, quite expensive for a very large graph. But however, if the graph has not very high degree nodes, or if in some way you cap the degree of these nodes, this again is very, very efficient. And as we show in our paper, it is possible with some preprocessing to do that on graphs that are extremely large. So now the theoretical guarantees, as I said, we can show that this method defines correctly the clusters. Now to make this more concrete, we need to define which clustering algorithm is used at the level of the EgoNet and the level of the global graph. So what I will do is that for the sake of proving this theorem, I will assume that we are using, again, the very simple connected component algorithms. So this is not the best clustering algorithm we can use, but it's very simple to reason in a mathematical way. So first of all, let's look at the probabilistic model that we define over which we want to identify the clusters. So the probabilistic model is the following. We are given n nodes on the left and k communities on the right. And these are like 2 parameters of the model. Then we induce a bipartite graph over these nodes in the following way. This is essentially a bipartite Erdős-Rényi graph, where for each pair of node and community, we add an edge with probability q, which is another parameter of the model. So this defines and encodes completely the overlapping structures of the graph, because notice that one node may belong to multiple communities, and this can completely overlap. Now that we have defined this, we create a graph among the nodes on the left, so a simple graph. And the way we do that is that we iterate over each community. We look at all the nodes that belong to that community, and for all these nodes, and for all pairs of nodes that belong to that community, we add an edge with probability p. So this is essentially an Erdős-Rényi graph over these nodes that belong to the community, and we do this for each community. Notice that if 2 nodes belong to multiple communities, you can create the edge multiple times, but in the end, we just take the simple graph, which is the union of all these Erdős-Rényi graphs. So now we have created a graph over the left side, and what we assume is that we are only given this graph. So now we don't know anything anymore about the communities. We only have this graph, which is the union of k Erdős-Rényi graph. We don't even know what k is. And our task is that we want to reconstruct the clusters. Of course, we cannot reconstruct the labels of the order of these clusters, but you just want to find these overlapping clusters. So this is the learning problem that we want to solve. And what we show is that even with this very simple connected component algorithm as the basis of our framework, for certain parameters of n, k, p, and q, it is possible to achieve in the limit perfect reconstruction. So what does it mean? It means that for n that goes to infinity, if p and q and k are a certain function of n, these algorithms converge to exactly outputting the correct clusters. More precisely, we show that the expected Jacquard similarity of the output of the clusters that we give and the original clusters is at least 1 minus these specific functions of p, n, and q, which is very hard to parse. So now I will just give you some concrete examples of scenarios in which these algorithms actually finds the correct answer. Let's assume that we have n communities. So the number of communities is the same as the number of nodes, and each community has a size order of c times log n. So it has a logarithmic size. And each node is part of log n communities. So we have like small communities, but each node is part of many of them. And each of these communities is actually a heterogeneous graph with the probability which is constant. So each edge is present with constant probability. If this is the case, we can show that the algorithms correctly identify these clusters. So another example is the one below, where instead there are again n communities, but these are very large. So they have a polynomial size with respect to the graph, and each node is part of many communities, so polynomial number of communities. And again, p needs to be 1 over n to a certain fraction of epsilon. But if for this specific range, again, we can identify the correct communities. So I don't have time to enter into details, but the way we show this is that essentially we show that these communities for these ranges of parameters are connected not only over in the original graph, but they are connected in each egonet. But the egonet splits them correctly. So each community is not connected in the wrong way. Now we give some examples. This is as they say, a picture is worth 1,000 words. So on the left side, there is a graph that I've created with a standard benchmark. And there are 100 nodes part of 9 overlapping communities. As you can see, it's very hard to tell which node is part of which community. And so this graph is plotted with the standard graph drawing tools. And the graph drawing tools, it asked the graph drawing tools to identify the clusters, and it didn't do a very good job. In fact, you can see it's not very clear what it identified. Then we created the persona graph, which is the graph on the right. This graph has more nodes, but the same number of edges. And now, with the same parameters of the drawing algorithm, it's very clear that this is a very easy to cluster graph. You don't even need an algorithm. You can do that by hand. And moreover, like even experimentally, you can see that the graph on the right has a much higher modularity. So it means it's easier to cluster. Now, why this is interesting? Because I think this shows that the persona graph creates an interesting exploits some interesting properties of the original graph and is able to disentangle the overlapping structures of the community. So potentially, you can imagine that you can use the persona graph as a first step to many other graph problems. Here on the right graph, it's clear that it's easier also to do ranking, not only clustering, but also semi-supervised learning, whatever is your favorite graph algorithm. Perhaps it's easier to solve that on the right side. So this is why I think it's an interesting result. Now, in terms of scalability, we have run this on several graphs that are, they're pretty large. The largest one is the clue web graph. It has 60 billion of edges. And for this graph, unfortunately, we don't have ground truth, so we'll not show any accuracy results. But for all the others, we have the ground truth thanks to the Snap library, which is a great resource. And we also use the synthetic graphs with the overlapping communities, and they have, of course, the ground truth. Then we compared using the standard F1 and NMI score with the demon algorithm, which was the previous egonet-based algorithm. OLP, which is an off-the-shelf overlapping label propagation algorithm, and also several non-overlapping clustering algorithms that I don't even report because they're very too poor results. Now, these are the results in synthetic benchmark. Our system completely outperforms all the others and gets close to 100% precision in recall and F1, etc. in some of these benchmarks. Then on the real-world graphs, again, we outperform all the others, but the precision and recall is much, much lower, which, of course, is a very hard problem in the real world, but still improve over the other results. Now, here I'm showing just the scalability. It shows that the running time grows way less than linearly in the size of the graph. This is the wall clock time using a very, very large-scale distributed system. So it shows it actually much better than what you would expect from the worst-case analysis. So now, in conclusion, we have shown it's possible to construct and cluster this very egonets of very large graphs with provable theoretical guarantees, and these are potential application in other works. As a future work, what we want to do is that we want to extend this work to other models of computation, for instance, dynamic graphs or stream graphs, and we also want to explore the properties of this persona graph and the potential application in other problems. Now, so thank you very much for your attention. If you have any question, I will be glad to answer. These are some of the contacts for me. And also, we have recently created a link for our Google team, which is the Google New York City Algorithms and Optimization team. So feel free to visit that website. Thank you.